Hi, we're StaRS FInE. I'm Whitney.
I'm Lily.
I'm Sam.
And we're developing a better way to extract water from stacked rapid sand filters. StaRS FInE stands for Stacked Rapid Sand Filter Injection and Extraction. We don't actually work with injection anymore, but past iterations of the team have developed the current inlet pipe. We're working on changing the slotted outlet pipes into a kind of branch design that you can see in this picture, because the current slotted pipes get clogged with chemical deposits and there's not really an easy way to clean them that doesn't involve shutting down at least part of the plant for a little bit of time. We have to be very conscious of major and minor head loss while we're doing these designs because we're one of the last steps in the overall process, and we're very integral for making sure that we get clean water out of the entire system. This figure shows some problems with air bubbles that we'll talk more about later, but you can see very clearly that there is a gravity exclusion zone formed, which is a fluid mechanics principle that says if the angle is steep enough, sand will fall down with gravity to a point where there's a clear water zone. And there you can see that.
So as for progress earlier this semester and in the fall, the main thing that we accomplished was printing the 3D filter that we would use in our apparatus here. We took a couple things into consideration when we were making it. The first was that it would actually function with gravity exclusion, so we would make the angle of inclination of the wings large enough so that sand could fall down them and that water could be in between these branches, and also that it could fit into our 4-inch PVC pipe apparatus, which is here in figure 2, where basically we would model it as like a bed of sand that had water where we could extract from the 3 outlet holes on the back side there. And this semester, the only changes we really made to this apparatus was adjusting the outlet hole size because we wanted to pull at faster rates, which requires larger tubing.
So the first 3 trials that we conducted had the setup that you can see in the picture here, where there's an injection pump and an extraction pump, where the injection pumps water into the bottom of the reactor and the extraction pump pulls water out of the 3 outlet tubes, which are corresponding to the 3 different gravity exclusion zones, which we were hoping would form. So as you can see here, that is another image of our reactor setup. And as you can see here, we have our first trial. So figure 6 shows that in our first trial, we inverted our reactor because we didn't like how the sand had fallen when we first put it in. But we didn't realize that that was completely basically preventing our exclusion zones from forming. Once the water pumped in, the bottommost branch was able to get an exclusion zone, and you can see in the video, which was playing before, that water is being pumped out, but in the topmost, there's sand, and that's because there's no exclusion zone, but in the bottom, there's only water, and so there's only water in the outlet tube.
Okay, so the main change for trial 2 was that we filled the apparatus with water first and then put sand in, which is the way that actual agua clara plants are set up. And we also had different flow rates that we recalculated with our Python code. You can see that the bottom tube has water all the way through it, and it did have a constant flow, but the top 2 branches had air bubbles that formed, and no water was being extracted from either of those branches for most of this trial. So it was encouraging that there wasn't sand coming out when all of the water was being pulled from the bottom branch, but it is still not exactly what we want to model because the whole point of experimenting was that all 3 zones could be tested. And also, we think that the glue wasn't exactly airtight or watertight, and that was part of the reason why these air bubbles were forming.
So in the 3rd trial, we're dealing with this problem with air bubbles and kind of extracting water at a really high rate. So what we decided to do is, considering the top two branches of the filter were like filled with air, that we would just plug them and try to pull all of the water out of the bottom extraction zone, which was consistently pulling water. And it was actually successful. Even at this super high rate of extraction, it was not pulling sand at all. It was just pulling water from the zone, and it was a super promising result. We obviously still have this air bubble problem, so we wanted to move forward by kind of equalizing this pressure, or figuring out a way to adjust it so that those wouldn't exist anymore.
So the big change for trial 4 was that we removed the extraction tubes completely, which we thought would be better to model the way that like gravity moves all of the water through the plant in an actual agua clara plant anyway, and there aren't electrically powered tubes, which is the whole beauty of our design. And we put a cap on because we were worried about the apparatus overflowing, but the problem with the cap was that it held the air bubbles in the top two branches, and so water was only coming out of the bottom branch still. And this was still encouraging because sand wasn't coming out, and we could have the entire injection flow rate coming out of just the bottom and have no sand come out, but still an issue with the pressure and air bubbles forming in the top two branches.
So in an effort to eliminate the air bubbles, we decided to remove the lid. And in order to fill up our reactor in this scenario, we found that we had to plug each hole with our fingers because there were no plugs that would fit into our specified hole size. And so as you can see in figure 16, there are fingers plugging the holes. And in figure 15, you can see what happens after we remove our fingers. The water level would fall pretty rapidly, as in it would not stay above the sand, and this is because we hypothesized because of head loss, because once the water was coming in through the inlet, it didn't have the energy to stay up above all three outlets, so the same amount of water that was coming in was also coming out, which was encouraging because it stayed at a steady state, and also sand did not exit with that. In this video, you can see, first of all, the water coming out, and now you can see that the gravity exclusion zones have formed, and there's also no air bubbles present. There's only water between those extraction zones.
So like Lily said, now we're dealing with this problem of head loss, so we decided that a good way to deal with this was to kind of submerge the whole system in water. But this is a tough task because we can't just put the whole apparatus underwater because it would be impossible to keep the sand down and kind of monitor how much water was coming out. So we devised a system where basically the whole filter would be underwater just by covering the outlet holes, and the whole injection and inner part was already submerged in water. So what we decided to do was design some kind of apparatus that would be closed on the bottom and open to the top that would cover the outlet holes. We ended up using a coagulant bottle that we cut in half and kind of curved to shape the apparatus so that it would be watertight, which we would then allow to fill up with water. As you can see in figure 21, once you filled it up with water, it was just pouring over the top. There was no sand in the outlet, and it was fairly successful. We're quite excited by these results, actually, because as you can see, as much water is coming out as is going in because of that steady water level right above the level of that cup there, and there was no sand in the effluent. The only problem with this really is that we can't tell which of the outlet holes that the water is coming from, but the whole flow rate that was coming in was at least coming out of one, and that's all that really matters. So as for conclusions from our semester so far, we're really excited from our results. We worked really hard to kind of model our apparatus to fit the real life conditions of the agua clara plant in hopes of implementing this in the future. So our next moves will be like to scale up and to kind of speak with Monroe and see where he wants to take this. All right, reach out to us with any questions.
Thank you.